Welcome to this video where we're going to have a look at a fairly unique system of 6 stars. Now it can be found in the constellation of Eridanus, that's where it's actually located, and you can see on the constellation chart there that's exactly where it is located. Now 6-star systems have been found before. The thing that makes this particularly unique is that it's a triplet of eclipsing binary stars. And we're going to have a look at that, or what an eclipsing binary star is as we go through. But then when you combine all three together, it makes it very, very unique. So multiple star systems are not particularly unique. We found lots of them. We've even found planets orbiting them. So binary stars, triple stars, 4 stars in a system, they're all orbiting a common centre of mass. We've found plenty of them. And as I just mentioned, we have also found another system that has 6 stars in, but it's not quite the same as this particular one. So this one here, it's made up of 3 close binary systems. So you've got A, B and C. That's 2 stars that are orbiting their common centre of mass. And then they themselves are then orbiting a common centre of mass of those systems themselves. And then a pair of those is orbiting another one, and they go around like that. So it's a fairly complicated system, but the point is there are 3 close binary systems there that are all orbiting in a common centre of mass, and they're all gravitationally bound to one another. Now, they are eclipsing binaries, so that means that as we look at the star, or look at the actual system itself, the stars themselves eclipse each other. They pass in front of one another, which blocks out some of their light. So it's very uniquely aligned that all 6 of those stars will pass in front of each other at some point, and it blocks out their light, which is very, very unusual. In fact, it's normally quite rare for you to have an eclipsing binary just in general, because it has to be orientated that their orbits are edge onto us and they pass in front of each other to block out the light. So to get 3 in one system that are all aligned like that is very rare, and obviously it's the only one we have so far. So the first pair, A, they orbit their common centre of mass in just over a day. So about 1.3 days it takes to orbit their centre of mass. You then have the second component of that group, which is C. That takes about 1.6 days to orbit their common centre of mass. Now those 2 pairs orbit the centre of mass of the 2 systems. So A and C orbit around whilst the individual stars in those groups are orbiting each other as well. Now that orbit takes about 4 years, so a wider orbit than the actual binaries themselves. So they take 4 years to go around, whilst the actual stars in the systems take just over a day to orbit each other. Now then the other one is a slightly wider one. It takes a bit longer to orbit the 2 stars, so about 8.2 days it takes for that system to orbit their common centre of mass, those 2 stars. That's kind of slightly disconnected from the other pair, because the other 2 pairs are closer together, they're orbiting their centre of mass. This third one, B, is a bit further away, and that's why it's not orbiting in that particular pair group. And the AC group orbit the B group about every 2,000 years. So this takes a much longer now, so you've gone up to a much wider orbit now. So it's actually on different scales really. You've got the very tight binary systems that are orbiting quite fast. You go further out, 2 of those binary systems are orbiting each other around 4 years, and then even further out you've got a pair of binaries and a single binary which are then orbiting their common centre of mass every 2,000 years. So a few different scales there really for orbital periods. Now this is what a eclipsing binary would look like if you looked at the brightness of the star. So normally we actually can't see the 2 stars. If we look at them with a telescope, we can't resolve each individual star. It's rare that we can. We can just see a single star because they're that far away. We can't pick out an individual one. What we can do is we can measure the brightness of that star, and we can work out when one star passes in front of the other. So when the 2 stars are at their maximum separation, like they're illustrated here, you've got the blue star on the right and the yellow star on the left there, you get the maximum brightness because both stars are contributing to the total brightness of what we can see. So if you have a look at the light curve on the right hand side, which is the relative brightness of that star against time, which is actually the same as phase. Phase is just one orbital period. Then when they're fully separated, you get the maximum brightness. Now, when they start to eclipse each other is when you get that dip in brightness. So when the when the smallest star is going to eclipse the largest one, that's when you get your largest dip. So the smallest star will pass in front of the larger one. You get the largest dip in brightness from that. And that is, if we're looking from Earth, it should pass in front. Then we move across to the smallest dip. That will be the opposite way around. So this is where you have a large star eclipsing the smaller star. So the larger star will block out all of the light from the small star, but because the star is smaller, it's contributing less light anyway. So actually, the contribution to the full brightness of the star is less. So it doesn't create such a large dip in brightness. Now, that is a single eclipsing binary star, but this is actually a light curve of 3 of those. These are all eclipsing each other in their own systems, but they're also orbiting themselves as well. So the total light curve, the combined light curve, is given here. And this was detected by TESS, which was originally set up for looking for transiting exoplanets. So this is looking for planets that pass in front of the stars. But one of the good things about these telescopes, same with the Kepler Space Telescope, is that it's also monitoring all different sorts of stars. So it can pick out variable stars, all other things, as well as just detecting planets. So this is how it was actually detected. Again, it wasn't seen individually, the stars. It was seen by the variation in brightness. And it looks a lot more complex, that one, than just a single eclipsing binary star. So it takes a little bit extra work to pull out all of those individual systems from that. Now, if you were going to point your telescope at this system, you're not going to see those, as we mentioned before. They're just not resolvable. And the only way you can detect these sorts of things is by looking at the variation in brightness from the star over time. That's how we know what these systems are. So unfortunately, we can't resolve these as it is. We can only detect them from variations in the light. So, have any planets been detected so far? Well, not in this system. So there's no planets in this system so far, unfortunately. However, there are planets in other multiple star systems. So we've found them around multiple stars. And the really interesting thing here, I suppose, is if there was a planet in this system, or if there are planets, like more than one, where would they likely be? Are they stable? How did they get there? Because when you've got this many stars in this system, the gravitational perturbations from that are likely to destabilise orbits. So is there long-term stability there for a planet to form? If it did get there, was it captured instead? And even if there is a planet there and it is long-term stable, what would it look like? If we were on that planet, what would the skies look like? What would our seasons be like? There's likely going to be locations on that configuration where the whole planet is going to be in full daylight for a very long period of time. You're not going to get constant days, constant years. There's going to be variation in the days, the seasons, years, everything like that. So it would make a very interesting location or planet to actually be on. So thank you for watching, and if you enjoy, then you can check out some of the other videos.